In this podcast episode, Dwarkesh interviews Reiner Pope, CEO of Maddox and former Google TPU architect, in a detailed Blackboard-style lecture covering the technical underpinnings of large language models, particularly focusing on model architecture, machine learning infrastructure, and the mechanics behind training and inference at scale. The conversation delves into batch size effects on latency and cost, mixture of experts and parallelism strategies, memory bandwidth and capacity constraints, the economics of training versus inference, sparse attention, and the implications of hardware design. They further explore analogies between cryptography and neural network design, reversible neural networks, and the practical trade-offs shaping current AI systems like GPT-5, Claude, and Gemini. The discussion opens by analyzing why certain API providers offer fast mode at a higher price, which boils down primarily to the impact of batch size on efficiency. Rather than serving one request at a time, inference is performed on batches containing thousands of tokens concurrently. The batch size directly influences memory bandwidth utilization and compute throughput when running transformer models on clusters like NVIDIA's Blackwell rack with 72 GPUs. Using a roofline model that balances memory fetch time and compute time, Reiner demonstrates that latency is bounded below by the time needed to read all model weights from memory. As batch size increases, weight fetch costs are amortized over more tokens, reducing the cost per token, while compute time grows linearly. The optimum batch size is typically in the order of a few thousand sequences, on the order of 2,000 microbatches, where the system transitions from memory bandwidth bound to compute bound. This balance depends sensitively on context length, sparsity, and hardware parameters such as flops and memory bandwidth. Very large batch sizes enable much more efficient utilization of hardware, driving down per-token inference costs significantly. The analysis shows that paying more for fast mode is effectively paying for smaller latency batches that deviate from this efficient balance. The KV, key-value cache, plays a critical role during autoregressive inference in transformers by storing intermediate attention vectors for past tokens to avoid recomputing them. This cache's memory footprint scales with the product of batch size and context length, and fetching from it consumes additional memory bandwidth. While attention computation contributes to compute load, memory access dominates the cost for large context lengths because each new token attends to the entire history stored in the cache. The KV cache fetch time contributes a linear term in batch size to memory costs, illustrating the importance of balancing batch size and context length to avoid memory bandwidth bottlenecks. Sparse attention architectures alter this scaling, potentially reducing memory fetch overhead by attending to fewer tokens, which could allow larger context lengths without prohibitive overhead. Sparse mixture of experts models activate only a fraction of the full parameter set per token, dramatically reducing compute requirements. For instance, DeepSeek's model activates around 37 billion parameters out of 700 billion total by engaging only 32 out of 256 experts per token. This ratio defines the model's sparsity and influences both compute cost and optimal batch size. Increasing sparsity allows for smaller compute per token, but requires larger batch sizes to maintain efficiency, as the computation is concentrated on fewer parameters, raising memory bandwidth requirements accordingly. The trade-off is empirically complex. Increasing sparsity can degrade model quality disproportionately compared to compute savings, although research suggests some sparse models match quality of dense ones with far fewer active parameters. Implementing sparsity efficiently demands expert parallelism, where each expert runs on separate GPUs within a rack. A typical NVIDIA Blackwell rack includes around 64 usable GPUs, and models with hundreds of experts allocate several experts per GPU. The communication pattern between GPUs is an all-to-all exchange because each token routed to experts may travel from any GPU to any other. This pattern fits well within a single rack due to high bandwidth, low latency NVIDIA switch connectivity, scale-up network. However, scaling mixture of experts across multiple racks introduces significant bottlenecks because cross-rack, scale-out bandwidth is much lower, about 8 times slower than intra-rack communication. This physical limitation constrains the maximum scale of sparse expert models deployable within the available interconnect topology. A rack is a physical hardware unit holding approximately 64 GPUs interconnected via high-speed switches and cables. Raptors face practical constraints on the number and density of cables, power delivery, cooling, and physical space, limiting intra-rack scale and forcing a hierarchy of network switches. While within a rack, NVSwitch enables efficient all-to-all communication with just 2 hops, rack-to-rack communication depends on slower data center networking. Recent NVIDIA architectures have increased scale-up domain size from 8 GPUs, Hopper, to over 500 GPUs, Rubin, but this required complex physical designs and cabling solutions. The benefit of increasing scale-up domains is mainly in improving aggregate memory bandwidth, enabling longer context lengths and lower latency inference by loading weights faster, rather than due to raw memory capacity, since capacity can be handled through pipelining. Pipeline parallelism divides the model's layers across racks or devices, processing sequential layers in a train-like schedule where multiple micro-batches are simultaneously in flight. This alleviates local memory capacity constraints by holding portions of the model on different hardware, but introduces pipeline bubbles, idle time due to serial dependencies, and requires micro-batching to keep all stages busy. While pipelining reduces memory footprint per device, weights are sharded across racks, it complicates caching and batch amortization because KV caches cannot be effectively shared or sharded across pipeline stages. This limitation means that KV cache memory requirements remain roughly constant per device, reducing the benefits of pipelining for KV capacity. In inference, pipelining neither improves nor degrades latency significantly, but helps with memory capacity constraints. Due to current surplus HBM per GPU compared to model and cache requirements, pipelining has limited benefits in frontier inference workloads, which typically favor expert parallelism within a scale-up domain. Memory bandwidth, the rate at which data can be moved into processing units from high-bandwidth memory, HBM, has become a decisive bottleneck for scaling models to very long contexts or huge parameter counts. Memory capacity, while large on modern racks, tens of terabytes, is less of a limit because pipelining can shard model weights across devices. Improvements in memory bandwidth have been slower relative to compute throughput, termed the memory wall. This fundamentally limits increases in context length because KV cache fetch scales linearly with context size and dominates latency and cost as contexts grow. Sparse attention techniques reduce this scaling, but only to a point, since excessive sparsity degrades model quality. The deployment of very large scale-up racks, like NVIDIA's Rubin, delivering 10 to 20 terabytes of HBM capacity with high bandwidth, is one reason very large models with long contexts have become feasible in recent years, enabling transitions from 8K to 100K plus token contexts. Reiner provides a heuristic framework to balance compute costs across pre-training, reinforcement learning, RL, and inference phases by equalizing their compute expenditure based on scalable laws and practical assumptions. The backward plus forward passes for training cost roughly 6 times a single forward pass, 2x forward, 4x backward, while RL involves generating tokens with less efficient training on rollouts. This model suggests that roughly the total token volume processed in pre-training, RL, and inference should be on the same order of magnitude over the model's lifecycle. For instance, with hundreds of millions of tokens per second served in inference and deployment cycles lasting months, the volume of tokens processed in pre-training and RL approximates the inference token volume, implying models are effectively overtrained relative to Chinchilla's compute optimal training tokens by a factor of around 100x. API pricing data from models like Gemini indicate a roughly 50% price increase for inputs exceeding 200,000 tokens of context, echoing the memory bandwidth computation crossover point in roofline analysis. By assuming this cost inflection corresponds to balanced compute and memory costs, one can back out estimates of KV cache storage per token in bytes, aligning with architectural parameters like number of attention heads and embedding dimensions. Price differences in input prefill versus output decode tokens, with decode often priced 3 to 5 times higher, reflect underlying compute and memory bottlenecks. Prefill is compute-dominated, while decode is memory bandwidth limited. Cache hit pricing, significantly cheaper than recomputation, corresponds to storing KV caches in fast, costly tiers of memory, HBM, and slower but cheaper tiers like DDR or flash storage, with storage duration influencing the cost of maintaining these caches. The KV cache's storage and retrieval costs differ by memory tier. HBM, DDR, flash, spinning disk, each with distinct capacities, bandwidth, and cost profiles. Fast tiers like HBM have minimal latency but limited capacity and high cost, while slower tiers offer vast capacity at the cost of increased retrieval latency. Systems must balance storing KV caches in these tiers based on expected reuse frequency and cost effectiveness. Analysis of cloud cost data suggests cache storage pricing aligns with multiple memory tiers, with tier eviction and retrieval times reflecting drain times of respective memory media. Slow tiers like spinning disk may incur hours for full capacity reload, highlighting challenges in maintaining large caches for extended contexts. Reiner explores intriguing conceptual parallels between cryptographic primitives and neural network architectures. Both processes perform transformations that mix information across inputs, but with opposite aims. Cryptography scrambles inputs to maximize entropy and obscurity, the avalanche effect, while neural networks seek to extract meaningful signal from noisy or random data. A key difference lies in the operation fields. Cryptographic ciphers typically operate over binary fields requiring discrete operations, whereas neural networks use differentiable real-valued functions optimized by gradient-based learning. Despite these differences, some concepts cross domains, such as differential cryptanalysis in crypto and adversarial attack analysis in neural nets. One fruitful crossover of cryptographic ideas into neural architectures is the notion of invertible transformations, exemplified by Feistel network constructions widely used in cryptography. This inspired reversible networks, RevNets, architectures whose layers are invertible functions, permitting reconstruction of inputs from outputs. RevNets enable major memory savings during training because instead of storing all intermediate activations for backpropagation, the activations can be recomputed, rematerialized on the fly by running the network backwards. This trades extra compute for drastically reduced memory footprint. Invertible transformer layers have thus been proposed to alleviate hardware memory limits during training, a complementary approach to caching strategies employed during inference, which trade memory to save compute.